Alright, Chapter 8, Exponential Logarithmic Functions. Alright, 8.1, exponential growth. Goal, growth is exponential growth. Exponential growth is a form of y equals a to the b, a times b to the x, where a is not equal to 0 and b is a positive number other than 1. If a is greater than 0 and b is greater than 1, this function is also such as a function as an exponential growth function because the values of y and x, y grows as x increases. To graph exponential functions, you make a table of values, plot their corresponding points shown below. Exponential graphs. Here are some characteristics of graphs where y equals a times b to the x, where a is greater than 0 and b is greater than 0. The graph rises from left to right. The graph passes 0a and 1ab. The main is all real numbers, and the range is y is greater than 0. An asymptotype is a line that graphs approach more and more closely with the y-axis. A symptotype graph like y, a, bx, a times b to the x. The graph times y equals a times b to the x, changing depending on the values of a to the b. Translating exponential functions, graph the exponential function y equals ab to the x minus h, or y equals ab to the x plus h. Plus k. Sketch of the graph of the function y is equal to ab to the x, and then translate graph horizontally by h units, vertical by k units. For example, the graph of the functions y equals 2x y equals 2 to the x minus 4 and y equals 2 to the x plus 3, shown below. The translation graph of y equals 2x. Exponential decay. Exponential decay has a form of y equals abx, where a is greater than 0 and 0 is less than b, but b is less than 1. For example, show the basic shape of the graph of the exponential decay function. Exponential decay graphs. There are some graphs of the y equals a times b to the x. A is greater than 0 and 0 is less than b, but b is less than 1. Graph falls from left to right. The graph passes 0a and 1ab. The domain is all real numbers, and the range of y is greater than 0. A3, modeling with exponential functions. Alright, you will use exponential growth function to calculate the balance. Some real-life quantities increase with decreased fixed percent each year over the time. The amount at y, such as quality after 10 years, can be modeled with the following equation. Exponential growth, y is equal to a times 1 plus r to the t. Exponential decay, y is equal to a times 1 minus r to the t. These models, a is the initial amount, r is the percent of the rate increase or decrease with its decimal. T is the number of time periods. The quantity 1 plus r is called the growth factor. 1 minus r is the decay factor. Writing exponential functions. Just as 2 points determine a line, 2 points can be determined exponential on the curve. Compound interest is an interest paid in initial investments called the principal. The previously earned interest earned is expressed in annual percentage. Interest usually compound more than once per year. Because the interest is usually compound more than once a year, the exponential growth year is equal to a times the exponential growth to the time period must be to modify the compound interest problems. Initial principal P is deposited in accounts and pays interest at an annual rate. R expressed in decimals. Compound n times per year. The amount of the account after t years can be modeled by the formula. The amount is equal to the principal times 1 plus the annual rate over the number of times per year to the number of times per year times the amount of years modeled. Continuous compounding, when interest is calculated as infinite number of corresponding compounding periods that will occur each year, is called continuous compound. The formula is continuous compound interest rate contains the formula E, like pi, and imaginary. The number E is denoted by a letter. The letter is called the natural base E, or Euler's number after the discovery of Leonard Euler. Natural base E is irrational, is defined as follows. The end of the approach is positive infinity. 1 is equal to 1 over the nth to the nth approaches a natural base of congruently 2.71828. At the nth approaches for the positive infinity, the compound interest formula that approximates the following formula: continuous compound interest. Compound interest formula approximates into continuous compound interest formula. 8.4 Logarithmic. Logarithms and logarithmic functions. Goal: evaluate the graph logarithmic functions. You know that 3 to the second equals 9, 3 to the third equals 27. However, what value of x does x to the x, 3 to the x, and equal 18? Because 3 to the squared is less than 18, and 18 is less than 3 cubed, you would expect it to be between 2 and 3. To find the exact value of the mathematician defined logarithms. So it reads x is equal to log 3, 18. Or it reads as log base 3 of 18, and which is roughly 2.631 congruently. Logarithm with a base of 10 is called a common logarithm and is noted by log 10 or simply by log. Or defining a logarithm with a base of base of b. B and y are positive numbers, such as b, so that b is not equal to 1. Logarithm of y with a base of b is denoted as logarithm of b. Logarithm with a base of b, y. Logarithm of y with a base of b is defined as follows: logarithm of y with a base of b is equal to x if and only if b to the x is equal to y. The definition tells you the equation that the logarithm of y to the base of b is equal to the b to the x, or equivalent. The first of the logarithmic form, and second is the exponential form. Given an equation, one of these forms you can write in the other form. For example, we'd have the log of 16 with a base of 2 is equal to 4, so it would be like exponential form 2. We would take the base at 16 and we'd give it the log of 2, and we found that its logarithmic form was 4. And special logarithmic values: let b be positive numbers such as b is not equal to 1. Logarithmic of 1. Logarithm of 1 with a base of b is 0 because is equal to 0 because b to the 0th power is equal to 1. Logarithm of base of b. Logarithm of b to the base of b is equal to 1, and b to the first is b. Inverse function: the logarithm of function gx of the logarithm of x is with a base of b is inverse exponential form of the function fx is equal to b to the x. This means the statements are true. The inverse function g of x with the logarithm of bx, b to the x with a base of b is equal to x, and inverse function f gx is equal to b to the logarithm of x to the base of b equal to x. Because exponential form of the logarithmic function or inverse function, you can graph the logarithmic function using, the exponential growth. Graph of y is equal to the log of x to the base of b is shown where the b is greater than 1. The graph of the y is equal to the log of x with a base of b, with a reflection of the graph of y is equal to the b to squared, b to the x, where the line is y equals to x. The graph of y is equal to the log of x, where the base of b includes ordered pair x in 0 and b in 1. The y-axis is a vertical asymptote. The domain is x is greater than 0, and the range is all real numbers. You can also graph translate the Logrithmic function to graph y is equal to the log of x and h to the base of b. Translate to the graph of y is equal to the log of x horizontally h units over the base of b. To graph y log equal to log x plus k is the log base of b. Translating the y equals log of x vertically and k units to the base of b. Alright, 8.5 properties of the logarithm. Because relationship, you will use logarithmic equations to explore this problem. Because of the relation between the logarithm and the exponents, logarithms have properties similar to the properties of the exponents. Let b, m, and m positive numbers such that b is not equal to 0. Product of logarithm m, the logarithm of m and n to the base of b is equal to the logarithm of m with the base of b plus the logarithm of n to the base of b. Quote and property, the logarithm of m over n to the base of b is equal to the logarithm of m to the base of b minus the logarithm of n to the base of b. And power property, the logarithm of m to the nth over the base of b is equal to the nth log of m to the base of b. You can use the property of the logarithm to expand condensed logarithmic expressions. Expand the expression sum of the difference of the logs. Expand a condensed expression, single log expression. When you do this, also assume all variables are positive. Eight 6. Solving exponential logarithmic equations. Goal: to solve the exponential logarithmic equations. Solve the exponential equations. You can use the property that has if the two powers with the same base are equal and their exponents must equal. Equal powers property. Base is greater than b is greater than 0, but b is not equal to 1, and bx if b to the x power is equal to b to the y, then x is equal to y. Alright, 8.6. Solving exponential logarithmic equations. Goal: to solve exponential logarithmic equations. To solve exponential equations, you can use property that appears. You can use the property if the two powers of the same base are equal and their exponents must be equal. So the equal powers property is that b is greater than 0 and b is not equal to 1. If bx is equal to by, then x plus is equal to y. So an example, if x to the 3 to the x is equal to 3 to the 5th, then x is equal to 5. It may not be convenient to write each side of the exponential equation using the same base. You can solve the equation by talking to the common logarithmic side. Alright, we'll look at the example 2. 3 to the x is equal to 5. 3 to the x is equal to 5. Write the original equation. Take a common logarithm from each side. X log 3x is equal to log of 5. So x with a log base of 3. The x log 3 is equal to log 5. Power property of logarithms. So x is equal to log of 5 over the log of 3. Using a divide calculator, each side by the log of 3, and you get 1.465. We'll show you another logarithmic each side. 10 to the x to the third, 10 to the x to x, n to 3 times x minus 1 is equal to 19. We rewrite the equation as taking common logarithm. Logarithm of 10 to the 3 to the x minus 1 is equal to logarithm of 19. We go log base, log of 10x is equal to x. So we have 3x minus 1 is equal to log of 19. 3x is equal to 1 plus the logarithm of 19. X is equal to 1 plus the logarithm of 19 over 3, 0, 7, 6, 0. Logarithm equations. To solve a logarithmic equation following the property of the logarithm with the same base. The positive numbers b and x and y where b is not equal to 1. Logarithm of x with a base of b is equal to logarithm of y with a base of b if and only if x is equal to y. Exponential each side of the equation. When one side of the equation is the logarithmic equation, you can exponentiate each side of the equation using each side of the equation as an exponent in an expression with the same base. For b is greater than 0 and b is not equal to 1, if x is equal to y, then b to the x is equal to the b to the y. And that's 8-6. Alright, Chapter 8 review. Chapter summary review. We've been on vocabulary terms: exponential function, exponential growth system, asymptom, exponential decay, growth factor, decay factor, natural base, common logarithm, logarithm of y with a base of b. 8.1 was exponential growth, exponential decay. Number 2, modeling exponents, exponential functions, logarithms, properties of logarithms, solving exponential logarithmic equations, Chapter 9, rational equations and functions.